Good morning, students. I am Dr. Shaktidharan. Today, I am going to cover the Unit 1 contents under the course Software Engineering in Artificial Intelligence. Okay, let's jump to the course directly. So, first, before we jump into the contents of the course, let's have a brief introduction of what the course is about. So first let's understand what a software engineering is. So software engineering is a specialized discipline that entirely focuses on developing a software. Before development we have to design it. So first designing and then developing and then implementing and then maintaining it throughout the life of the particular software. So in your previous semesters you would have studied about this software engineering and project management and other things. So all those things all those knowledge you can bring it to here, but the only difference is we are going to focus more on the AI implementation side of the software. So let's say we almost everything that comes umbrella of the application apps and other web apps, progressive web apps, everything whatever you have been installing in your over the operating system, those are considered as a softwares. So and a system software is a software that maintains the whole thing entirely, including the operating system. So there is a difference between application software and system software. So the key components of the system softwares are the basic. First, every software is going to run on the hardware. So over the hardware what we are going to have, so we will be having the operating system. The operating system is the core software that runs over the hardware. So for the operating system to access the other devices that's not the part of the particular computer, so let's say all the accessories you are having that connected to the computer, those can be called as accessories. So for that, to control those accessories, the operating system relies on the device drivers. So and then the utility programs, whatever the additional softwares then comes with the operating system. In other words, the stock softwares or the stock applications. For example, in your Android app, the clock application is a stock app. So let's say all the other applications that completely relevant and tightly coupled with the operating system. For example, task managers, service managers, and the hardware manager software, and all these things comes under utilities. So these are actually, in simple words, almost every software or every system software in the world will have a generalized common utility programs. And then we have a middleware. These middlewares acts as a bridge between the operating system and other applications that not necessarily to run inside the same machine. For example, a database system. So a database system can be living in a separate place, but at the same time it can be tightly coupled with the software or tightly coupled with your computer, so that your computer access those content from the other devices easily. And sometimes the middlewares we can consider as softwares, kind of a mixed term. It not actually a system software, but a kind of a software that runs between or acts as a bridge between the OS and the other systems. So the problem space in the system software engineering. Actually, I don't want to cover all those things because these things are very like a very foundational brief for the software engineering. We are going to focus more on the software engineering rather than focusing more inside the system software engineering. Okay, so understanding the problem domains. So for a system software, how it is developed, what is the end goal of developing it? So first we have to find all the requirements, and then we have to identify the constraints, especially the hardware limitations and other constraints like policy management, privacy issues, blah blah blah. And then we have to analyze the workflows, how the users are going to use this software for their real world use cases. So all these things comes under the things that we have to consider before developing this system software. So actually, as I said, to develop these softwares, including the system softwares and also the application softwares which runs over the system software, for example, in an example case, it can run, so the applications you install on the OS. So it goes under these kind of segments, where first you need to design the architecture where the system software is going to run, and then you have to focus on the developing cycle, like first the system development cycle, and then there are other methodologies that you are going to, different methodologies you are going to use to develop this. For example, agile methodologies or DevOps, etc. So finally the quality assurance, so the guarantee you're giving to your software. So we cannot, at least I'm speaking before the age of AI, so we cannot do everything at once. So as the system software is very complex, we are going to divide them into modular breakdowns, and then we are going to extract the abstractions layers and patterns that covers all the workflows inside the development, and then the algorithmic selection. For example, if we need to access the processes, and we are trying to run multiple processes inside a single processor, then we have to allocate time for the processor to run each process in a different time or in a different method, scenario or sequence. So for this sequence, we are going to, in your data structure you would have studied about this scheduling algorithm also in the operating system course. So these, what kind of scheduling algorithm that is suitable for the particular case, for this case, for a different case. For example, for a memory management, we can be using a different scheduling algorithm. For processors, you can use another scheduling algorithm. So different algorithms for reading and writing, for sharing and whatever it is. Okay, then the testing and refinements. So the real world impact. What would be the real world impact? So the ultimate goal is a user using a software without knowing that they are using it. So eventually it comes into their flow that they are going to use it. The design should be intuitive. You could not refer a manual each and every time when you do something with your software. So again, it has to give a proper flowy experience to the user. Second, it should adapt to not any infrastructure. For example, the infrastructure is available. So today a system software can run in a phone, can run in a PC, can run in a server, can run in a big data center, can run in a cloud, etc., etc. So again, the system softwares are not limited to the systems that have a visual interfaces. There are other systems that doesn't have visual interfaces, for example IoT devices. So for them also we can have a system software engineering. So we are not going to cover this future trends. I am leaving it to your perusal. The PDF version of this presentation will be shared with you, so you can refer these points. So we just directly jump to the system software platforms. So what are the platforms? So we have already covered all these things as a brief thing, so we are not going deep into these things. So let's see. So how the future of this particular system software. So these system softwares are required to adapt to the latest needs. The first need, it should go in hand with all the new trending AI and machine learning things. Secondly, in the age of this privacy and other things, personal matters that need to be secured, also every data is important, because today's data are very costly thing, right? The whoever having a data, a more relevant information, they rule the world. So our system software should be have focused on the enhanced security. So again, it should adapt to the cloud and distributing computing, and then it has to adapt, whenever a new devices or new softwares or new things like a AI bubble that comes, right, that has to adapt to those things. So in the conclusion, the system softwares are undeniably the indispensable backbone of the digital existence. Wherever you go, wherever the devices you need to help you, or that you need to utilize a device, it needs a system software, especially all the digital devices. So that's it. So it has an indispensable role. It need to have a harmonious operation along with, it sits as a bridge between the hardware and the user, right? User means people. So, and it needs to progress, it needs to be robust, it needs to update, it needs to get upgraded. So every 6 months Android is giving an upgrade, every few months iOS is giving the upgrade, every few months Windows OS is getting updated. So those things. So now we are coming to the real part, that is comes under the system software. The first two things we are going to cover briefly in this first unit is virtualization and then containerization. Virtualization is very simple thing. So we have this idea, so we have a hardware, so one system software can run in a one single hardware. So in here hardware is a collection of components. For example, a PC has components like processor, RAMs and storage devices. So all these things considered as a one device. So the virtualization proposes a model where a one device can virtually act as a multiple device. So that's how it works. So we are going to have a one big hardware, which that hardware is going to simulate a virtualized hardware device, where the simulated hardware device is not actually a hardware, it's a simulated hardware where a system software can run. So the system software thinks the virtualized hardware as a real hardware. So from our point of view, we can maintain one big hardware to create multiple virtualized hardwares. Later this concept is expanded where we can have multiple hardwares, for example multiple storage devices can act as a one single storage device. Let me give you an example of a Google Drive. You see Google Drive as a one drive or as a one folder. Within that folder, whatever data you want to put, you can put. But if you see in the data center's end, that is a back end, where those things, actually these data centers doesn't run with a one single hard disk, right? So it will have a multiple hardware, where a system software will project these multiple hardware as a single hardware to you. So whenever you put a data, whenever you upload a file in this drive, it is going to be saved in one of the hard disk. All the files of yours within your Google Drive that not necessarily have to be stored within one single hard disk. It may be spreaded across multiple hardwares, but the system software makes it look like a single folder or a single drive inside your account. So this is another example for a virtualization. So let's not focus on the system as a software, let's focus on other things. So one of the very commonly used virtualization is hypervisor. So hypervisor is kind of a middleware software which can create or simulate a virtual machines. Again, it's a virtual machine. So a single hardware which runs the hypervisor, where the hypervisor can simulate multiple virtual machines. In that multiple virtual machine, in each machine you can run a individual OS separately, where that OS environment looks like it runs in a single hardware, but originally all the multiple hypervisors are running on a one single real physical hardware. So that's the major difference. So why virtualization? Basically efficiency, then cost reduction, and simplified management. You think about efficiency, one system may, like one hardware is, if one hardware is not enough for a one virtual machine, we can add another physical hardware and make it look like a one physical machine, but one virtual machine. But because you have a two physical hardware below, then it can power the virtual machine multiple times. So whenever you don't need that kind of a power, you can turn off a one machine and these virtual machines can run in a one physical hardware. So that also saves in cost. And simplified management. So you are not going, let's take the same example as a Google Drive. You don't have to manage those data centers, you don't have to maintain it, you don't have to install any security softwares in it, you don't have to upgrade it. So whatever things you want to maintain the propagation of the particular service, you don't have to do anything. All you are going to do is log in and access. So for the other end, it is easy for them to manage in a single data center, right? So it's a simplified management. And what are the challenges? So let's assume what are the challenges it solved, what is the problems it solved. So wasted capacity. Let's say you need only 50% of a hardware. For that 15%, you need to buy a single hardware. You bought it and you are using it, but you are using to its maximum capacity of 15%. That means the remaining 85% stays useless. So actually you are paying for that 85% also, right? So when we have a virtual machine, you can create a virtual machine with a capacity of a 20%, and with that 24% virtual machine you can install a OS and you can access or you can utilize the 15% that you needed. The remaining 80% can be allocated to another virtual machine where some other user can put their OS and they can use it for their use. So this sharing helps in reducing the wastages. So and when two people share a one single hardware, the operational cost actually reduces, right? You don't have to, you can share the EB bill, you can share the server cost, etc. So and it also makes the infrastructure flexible. If you want to immediately upgrade the infrastructure, all you do is you can add few more hardwares to it, or if you don't need that kind of power, you can turn off those hardwares or something like that. Okay, so what are the types of virtualization? One is a server virtualization, where you can virtualize a server And then, so for example, shared hosting. uh, I know few of you or few of from our class is using a, I mean, have blogs and deployed websites, right? Simple websites. You, for reduced cost, you are using a shared hosting. That means the servers are virtualized, where you will get a small portion of the server, but technically you are not using a physical server, but you are putting or you are installing your server OS in a virtualized server environment. So again, when you do anything with this virtualized environment, it is not going to affect the other virtualized machines. That means the other people data or other people functions or processes are not going to affect if something happens in this one machine. So, and then application and desktop virtualization. Again, this comes under as a platform as a service, and storage virtualization, storage as a service. Google Drive is one of the good example. Network virtualization, virtual private network, VPN. I know most of you have used those VPN for streaming services, right? So those are the types of virtualization. Okay, and so let's not go deep into these things. These are the brief introduction of a virtualization, where you can go through this all data for your exam point of view. So let's jump directly to containerization. So in the virtualization, we virtualized machines. Here we are going to sandbox the environment. That means in one operating system, we can create multiple containers, so that each container can have its own software, and these containers works like a sandbox. You know the analogy, right? A sandbox is a box full of sand where a kid can play. When a kid play inside the sandbox, it is safe for the kid, because for the sake of playing in the sandbox sand, you don't have to take your child to a park where any harms can happen to the child. And in other advantages, if anything happens inside the sandbox, it is going to stay inside the sandbox. The sands are not going to spill outside the sandbox. That's an analogy for this concept. So if anything happens inside the containerized environment, if any software is like stuck somewhere, right, it is not going to affect other containers. And one more advantage of this containerization is, if you develop something and try to execute that in your device, it actually works perfect for your testing purposes. But when you export the code and deploy it in some other machine, obviously that some other machine is going to have a different environment than the environment you developed in. So you cannot simulate all the variables and take those variables, export to that new environment, because the new environment will be having a different software, different OS, different hardware, right? So the deployed software may behave differently because the environment is not the same. So the containerization also solve this problem, where whatever the software you developed within a container, you can take the container and you are going to put the container in the next machine, because the machine is not going to take the software as it is. The machine is going to simulate a container, and this container is going to have a same environment variables that is similar to whatever the environment you developed with. So it is going to work perfectly as it worked in your devices, right? So that's how the containerization works, and those are the advantages of the containerizations. So a containerization for containers, it can have a shared kernel, but it will have a different containers. Each container has its own different environment variables, and it is self-contained. So when I say it is self-contained, whatever the dependencies, whatever the additional softwares, codes, libraries that need to run those software, all those are packed into one package and put it in the container. So to run a particular software, you don't need anything from the operating system side, or you don't have to install any drivers, you don't have to install any additional environment in your operating system, but whatever the environment things or dependencies needed for the particular software to run, it is already contained within that container. So that's how it works. So these are the things the containerization concept solves. First, encapsulation. It encapsulates everything that need for the software to run. Second, it runs in a lightweight container. Third, it prevent conflicts. So, and one more example is whenever you go for another upgrade, right? Let's say increment upgrade, you are changing few codes in your code base. So it can create another container for this new upgraded version, and you can put it in this code container, so that the previous container works as it is. Once you are ready with the deployment of this container, you can deploy immediately this code into a new container space. Basically, you are taking a package and putting a new package inside. If anything conflicting, right, you can take it away and you can reverse the containers. So that's how it works. So I said, right, we can easily switch the packages. That's the concept of portability. So moving code, deploying code, upgrading code, all these things can be very efficient. You don't have to deal with the conflict management and other things. And scalability. Let's assume we have a one container, suddenly the usage increases, we can create another container, it's a clone container, have a same code base. Whatever the package you are installed in a container 1, it can be installed in a container 2 right now. So the two containers can serve the same purpose. So actually you scaled the efficiency of the containers, right? Efficiency of the software, the number of services it can give. So, and fault isolation, if anything happens inside the code base, you can actually isolate what happened, because actually it is running in an environment that is the same environment installed in the, having the another container is having the same environment. So if you move the code there, and if you find any bug, the same bug is going to stay in the same place in the package 1 container, container 1 also, right? So it is easy to identify the faults. So maybe there are sometimes the fault may be in the hardware side, but we may be trying to debug in the software side, because we assume, because the particular software is moved to the new environment, we assume it is not fitting to that new environment. Actually it is running perfectly as a software, but maybe some dependencies or some other hardware dependencies might not work there. So when you use a container, you can easily isolate whether it is a hardware or a dependency problem or a software or a business logic. So, and microservices and support. So nowadays all the microservices using this containers concept. So I can give few examples. For example, the Uber is having multiple containers running. So and let me give another use case where a large university is publishing a result, right? They can use this kind of techniques, because they can increase the number of containers to serve the students surge of checking their marks immediately within 1 day or 2 days. After the surge is reduced, right, you can switch off few containers. So those things, examples. So this is how containers. So it's not an exact architecture of the container, but you can see the tiers of components or software components. So first, physical infrastructure is in a dark blue color, and the medium blue is host and system software, mainly OS, and over that the navy blue color represents the containers. Here the containers are self-contained things. So these are the tier layer architecture. But assume within this running containers, you will have a multiple containers having multiple copies of a container packages. So as I said, this has been adapted by leading tech giants, and from the leading tech giants to a bottom simple app developments, they are all using containers. And one of the container service software, the software that needs to simulate a container and maintain it, those softwares, for example, the leading software is Docker and the Kubernetes. Let's talk about the Docker and Kubernetes, how it is work. Let's implement few Docker and Kubernetes containers in our lab time. Thank you, students. Let's meet on the unit 2.